Okay, chapter 11, reactions and properties of organic compounds. So first of all, we look at some of the properties and the trends in those properties of organic compounds. We need to just quickly revise our intermolecular bonding, because it's like we found early on in the year with the fuel stuff. All the interactions between molecules can be explained by the strength of intermolecular bonding. So stronger intermolecular bonding means higher melting and boiling point, means more viscous liquids, means higher flash points for flammable liquids. You have to heat it higher before you get enough vapour to sustain ignition. And stronger intermolecular bonding is going to be caused by polarity, which ends up resulting in solubility in polar solvents. So of course, everything has dispersion forces between it. Those attractions, random attractions, when you get an imbalance in electrons around a molecule, random attractions between the electrons in one molecule and the nucleus of another. The weakest form of intermolecular bonding, found in everything. And proportional to the number of electrons. We'll commonly say proportional to the number of carbons, proportional to the molar mass, etc. But essentially it's coming down to the number of electrons. Closer packing means stronger intermolecular bond, stronger dispersion forces. Larger surface area means more contact between molecules, means stronger dispersion forces. Branched molecules, because they don't pack as tightly, have weaker dispersion forces. Dipole interactions, but when you get polar molecules, you get additional attractions on top of the dispersion forces. Because you've got a permanent dipole, you have a positive and a negative end of a molecule. Those can attract each other. And often they're not that significant. They just add a little bit to the strength of dispersion forces. Hydrogen bonding is the big one, of course. For our purposes, we're simply talking about OHs and NHs. FHs is very rarely encountered. So when that happens, you've got the strongly electronegative oxygen or nitrogen pulling the hydrogen electron towards it, leaving that naked hydrogen nucleus exposed to the chemical environment, able to get close to any other lone pair of electrons it can find. So a stronger polar interaction, and that leads to higher melting and boiling points, solubility, because water, of course, has got lots of hydrogen bonding. It means it's going to mix with water easily. So you've got the lone pair on the oxygen, and you've got the naked hydrogen with its electron being pulled away by the oxygen. So you get a moderately strong hydrogen bond formed. Okay, boiling points and solubilities of organic compounds. Now, hydrocarbons. If you've only got carbons and hydrogens, any molecule with just hydrogens and carbons is non-polar, only has dispersion forces. End of story. So that means low boiling point, completely insoluble in polar solvents. Boiling point increases simply with molar mass as the dispersion forces increase. As I say, completely insoluble with water. Haloalkanes, weakly polar. You've only got that one halo group usually, a chloro or a bromo or something. So there is a small amount of dipole bonding, a little higher boiling point because the intermolecular bonding is a little bit stronger. The dipole bonding adds a little bit to the dispersion forces, but not a huge amount. Significant when you've got molecules with a similar molar mass. Solubility, very slight solubility in water, but they much prefer non-polar solvents. Alcohols, amines, amides, strongly polar because they all contain hydrogen bonding. Alcohols have got an LH group, amines have got NH groups, amides have got NH groups. If we look at the trend in boiling points of alcohols, we see they've got much higher boiling point. We're talking about degrees Celsius there, so much higher boiling point than a hydrocarbon of a similar molar mass. Methanol is the same as ethane. Ethane boils at somewhere around minus 100, I think, whereas methanol boils at around 60. What's a zero carbon alcohol? Well, water, of course. And we see the molar mass, as the number of carbons increases, the molar mass increases. That means stronger dispersion forces, and you can see the effect that that has. Because primary alcohols, you've got the hydroxyl group right at the end of the molecule, easily accessible to anything else. So you get stronger hydrogen bonding, therefore a higher boiling point. So secondary and tertiary alcohols, with the hydroxyl group being covered up a little bit more, have lower boiling points. Branched molecules also don't pack as closely. Carboxylic acids, again, strongly polar, contain hydrogen bonds, even form ions in aqueous solution. And there is that formation of a dimer. Two carboxylic acid molecules pair up with each other, and you get hydrogen bonds formed between adjacent carboxyl groups. So the oxygen, the carbonyl group on one, forms a hydrogen bond with a proton on another, and vice versa. So that's a reasonably stable arrangement, and it effectively gives the unit a higher molar mass, therefore higher boiling point. Boiling point, of course, increases with molar mass, like with everything. Esters, aldehydes and ketones are polar molecules. They don't have OH or NHs, so they don't have hydrogen bonds, but they've got significant polarity. So higher boiling point than alkanes or haloalkanes, but a lower boiling point than acids, alcohols and amines. And we see the table there. So carboxylic acids with the dimer formation has got the highest boiling point. We've got a group of molecules all with a similar molar mass. So then we come down to alcohols having stronger hydrogen bonding than amines. It's interesting that the hydrogen bonding from the amine compared to the ketone is not that significant. Then down to the ester and then the chloroalkanes and the alkanes. Solubility in water. All of these molecules can interact with the water molecule. So a polar group interacts with water molecule, attracts water molecules, therefore is going to be water soluble to some extent. And that's the case, but as the number of carbons increases, you get a longer and longer hydrophobic carbon chain. It becomes less and less soluble in water. So the strength of the hydrogen bonding in water is sort of up against the hydrocarbon bits would much rather be connected to each other than the water. The water would much rather be attracted to other water molecules than the hydrocarbon. So as the number of carbons gets bigger, the solubility decreases. Larger non-polar hydrocarbon group, bigger the hydrophobic effect, the lower the solubility. So 1, 2 or 3 carbons, you can dissolve as much alcohol as you like. Butanol, 4 carbons, has got high solubility, looks like 8 grams per 100 grams of water, but that rapidly decreases to the point where decanol is barely soluble at all. Yeah, trend in non-polar solvents is the opposite trend. So methanol and ethanol are poorly soluble in non-polar solvents like hexane, but by the time you get up here, they're completely soluble, completely miscible. Viscosity, the resistance to flow of a liquid. So compare the classic high viscosity liquid is honey. You pour honey, it flows very slowly. Compare that to a liquid with low viscosity like water. Water is probably not the best example actually. Think of petrol, although we don't sort of tip petrol around as much. But comparatively, water has a much lower viscosity than honey because it flows much more slowly. Honey has a much higher resistance to flow. And again, it's all to do with the intermolecular bonding, with the strength and particularly the number of interactions between molecules. So, as I was just saying, petrol actually has a much lower viscosity than water. If you spill petrol when you're filling up a car, it splashes much more sort of widely than than water does. And that's because petrol's only got dispersion forces, it's a hydrocarbon. Water, of course, has got hydrogen bonds. Dispersion forces are much weaker than hydrogen bonds. Now with hydrocarbons, non-polar hydrocarbons, we've only got dispersion forces. As the strength of those dispersion forces increase with molar mass, the viscosity does. So petrol compared to kerosene compared to motor oil, viscosity increases enormously, increasing strength of dispersion forces. It also increases with the number of interacting functional groups. So number of hydroxyl groups is an interesting one. Water has got 1 hydroxyl group, so moderately low viscosity. Ethylene glycol, which has got 2 carbons and 2 hydroxyl groups, so 2 hydrogen bonding sites, straight away the viscosity increases enormously. Sugar syrup, depending on what sort of sugar it is, has between 5 and 10 hydrogen bonding sites, viscosity of almost 1400. Compare that to honey, which has got a lower proportion of water, so a bigger interaction between all those hydrogen bonding sites has got a huge viscosity. More hydrogen bonds, high viscosity. More hydroxyl groups, higher viscosity. Flashpoint. So any liquid at any temperature produces vapour. If it's a flammable liquid, the temperature at which it produces enough vapour for ignition to be able to, for a flame to be able to be ignited, is known as its flash point. Now, just note the process that happens when you light a candle. It's not the solid wax that's burning, it's not the liquid wax that's climbing up the wick that burns, it's actually the wax vapour which is released into the atmosphere that burns. So you have to get that vapour. So as you light the candle, you provide enough heat to vaporise a little bit of wax, and the flame is sustained. Some substances produce vapour more readily than others. So ethanol has a lower boiling point, weaker intermolecular forces. Its flash point is 14 degrees. So all those flammable drinks, those flammable puddings, etc., that's because of the low flash point of ethanol. Cooking oil, you've got to heat cooking oil very hot before you'll get flash point. So if you're deep frying and the oil gets to above 325 degrees, then you're in grave danger of having a really serious fire, because at that temperature you've got enough vapour to sustain flame. So weaker intermolecular forces, lower flash point, related to the lower boiling point, because you've got a higher vapour pressure at any particular temperature. Okay, do these questions and submit the answers online.